So are there any ideas on how I can do this problem with fractions in it? Do you remember what to do? Common denominator. What is the common denominator? So it's right, exactly. It's 4 times x plus 4. So we do that on all of the fractions in the numerator, plus we have to do it in the denominator. That was next door, Coach Thomas's room. All right, so we have some things that cancel. So what am I going to have on top? Looks like what? 4 minus parentheses x plus 4. Do y'all agree with that? I think that's right. Okay, if you add like terms, what will that end up being? Are you sure it's going to be x? Negative x, because it's 4, change the sign, and we're left with negative x. So that's a little different than what we're used to seeing, but if you don't take that into account, your entire problem will be wrong. What do I do now? Cancel out the x's. Am I ready to substitute now? Yes. So what's on the numerator? Negative 1. Substitute 0 into x, and we get negative 1 over 8. Now remember, the whole point of all of this limit stuff, the reason we even do it in the first place, is that on that problem, I know the domain is x can't be 0. In other words, f of 0 is not defined. Right? But if I do this limit at 0 for that function, and I get negative 1/8, what does all of that put together mean? There is a hole where? There is a hole at 0, negative 1/8. That is the entire reason why we do this. Yes. Oh, yes. 4 times 4 is 16 the last time I checked. Yes, thank you. Yeah. Yeah. I can do calculus, but I can't do arithmetic. So. All right. All right. Yeah, that looks a little better. All right. Questions about that? All right. So just to be sure that we're okay on the other factoring problems, let's do a quick review problem here and there, and then we'll look to some of the oddball ones that are in the book. Now, one of the things that's in your notes, and our book even mentions this, there's this theorem that says functions that agree at all but one point. If you'll flip back a page or two. Now, in essence, what this is telling you is first, remember that some functions don't have limits. Sometimes you'll do a limit and you get does not exist. But it's reminding you about what do you do when you get 0 over 0. And Lauren, what did you tell me that 0 over 0 was? Indeterminate form. So when you encounter an indeterminate form, what have you got to do? Do something. You might have to factor. You might have to do synthetic division. You might have to rationalize the denominator. You might have to multiply by the common denominator. There's several things that you might have to do, but do something. Now, the reason this works because of this theorem, like on this problem here, you have been taught to factor this and cancel, right? Why does this work? Well, the reason this works is that this function and g, let's call the original problem f of x, and let's call this new one g of x. Okay, so let's factor this. Do you see the 2x squared here? What does that mean as far as factoring goes? 2x and x, right? What does the second sign being negative mean? Different signs. However, here's your hint, guys. If this says x plus 1, 9 times out of 10, guess what's going to be up here in the numerator? X plus 1. So if I know the signs are different, what's this going to be? Minus 3. And so that cancels. Here's what this theorem is telling us. This function and this function agree everywhere except at one point. What one point do they not share? The negative 1, because this has a domain issue, right? This one does not. But what that limit theorem tells us is that if two functions agree at everywhere but one point, you can do the limit of this function and you'll be all right. That's why all this stuff works that we've been doing. Because those two equations, those two functions agree everywhere, but in this case at negative 1. And then you can just do direct substitution, and you get the answer at negative 5. And what does that answer really tell us on this? There's a hole at negative 1, negative 5. Because of the fact we have this domain problem. Now, don't think this, though, because this is a common misconception here. Take this limit. Clearly, that's 4, isn't it? Does that mean there's a hole at 2, 4? No. Why? There's not a domain issue there, right? Yeah, it's defined there. That just tells you there's a point there. There's a point at 2, 4. So just make sure you don't make that mistake. Yes. Yes. All right. All right. Rationalizing the denominator. Let's do one more like this. Make sure you know what to do. What do I multiply by here? Not x square root plus 2. We got to multiply by the conjugate, right? In this case, we're not rationalizing the denominator, we're rationalizing the numerator. What do we always get when we multiply by the conjugate? Difference of two squares. Excellent. So I've got a minus b and a plus b. So I have a whole bunch of junk in the denominator. All we can do right now is just write all that mess down. Tell me, what am I going to get in the numerator? A squared. No, I'm going to get a squared minus b squared, right? So what will that be? X plus 1 minus 4. Which, what is x plus 1 minus 4? X minus 3, right? I'm just going to put it right here because I don't want to write all that over. So what do I do now? Cancel. Substitute it in. Yeah, I can do direct substitution now. But there's an understood 1 in the numerator. And so if I substitute 3 in, it looks like, what am I get, 1/4? It's all just coming back to you. Come on back. All right. So now the only thing that's new, because you know last year we did factoring, we did the fraction problems, we did these square root problems. The only two things that's really new are the trig problems, and then one other thing I've got to go over today called the squeeze theorem. That's the only two things that are new. So let's go to the trig problems. If you'll turn over, find where, go over a couple of pages where you see our two trig limit problems. Now, in a minute, I'm going to show you another reason why these two limits are true. You know, yesterday we talked about that we could demonstrate on the calculator why they're true, but I'm going to show you an even better way of showing why they're true. But we're going to get to that in a minute. Let's do a couple of problems to make sure we're kind of on track here. Now, we've already done both of these. We did these yesterday. So I want to change it up just a little bit to make these a little bit different. What if this had have said tangent of 2x over x? Let's make it a little different. What did y'all do yesterday on that problem? Sine over cosine. But we're not going to put sine of x over cosine of x. What am I going to put? Excellent. We're going to put sine of 2x over cosine of 2x. What do I do now? Multiply by the reciprocal, right? 1 over x. Now, as of right this second, I almost have it like that first limit. The limit as x approaches 0 of sine of x over x is 1, but I don't have it quite there. So what did we learn that we could do yesterday? The commutative property, right? So what did we do with the commutative property? Excellent. All right, so I want my x here, and I want my cosine 2x here. Now that's what we did yesterday. However, I've got to do something extra today because that's still not exactly right. All right, so I'm hearing I need to put 2 right here and put 2 in front of the sign, or I could, is it okay to put 2 here? Commutative property, right? I can put the 2 anywhere up there I want. If you want to put it in front of the sign, that's fine. If you want to put it to the side, that's fine too. Now, this next step, I'm going to write because I want to make sure everybody understands why this is legal. But one of the properties of limits is that when you have two functions multiplied by each other, you can do the limit of the first function and then multiply it by the limit of the second function. Now, normally we would not write this step out, but I want to make sure you understand why what I'm about to do is going to work. That's why. So what is the limit of this stuff right here? Based on this theorem, exactly right. It is 1. How am I going to do this limit? Substitution. So I have 2 on top. I'm going to substitute 0 into the x, and I need to know what cosine of 0 is. It's not negative 1. It's 1. See? Right. See right here? It's 0. That's 1. Cosine of 0 is 1. So that answer is going to be 2. All right. Well, if you'd have put it in front of the sine of 2x, you'd have had to have said that this right here was 2. Like if you'd have put the 2 here, you know, that's 1, but that's 2. 2 times 1 is 2. Other side would have been 1, right? You'd have done it that way. All right, this next example. Now, we did this one yesterday, so I want to make this different. That's too easy now. Let's add that to the bottom of it. Make that a little harder. Any ideas? Now remember, you can't factor out on sines and cosines like sine of 2x. Remember, it's 2 sine x cosine x. I mean, you got to do identities, so you can't really factor per se. No, not least common multiple. You're nothing that fancy. Can't cancel. That is a common mistake, though. Some people will think you can cancel 4x and 2x. Split it apart. Yes. Split it apart. How, though? Yes, that's exactly what you do. We want 2 fractions. We're going to put sine of 4x in the numerator of one fraction, sine of 2x in the denominator of the other one. That's exactly right, Audrey. Very good. Now, remember my little formulas. Something I haven't told you yet, but we could easily prove. And you might want to jot this down at the top. But not only is this equal to 1, but the reciprocal is equal to 1 as well. Alright, that's equal to 1 as well. So the fact that that's upside down on our problem is not going to really matter. But all of that's true. If you think about it, it makes sense because it's just 1 over that. So 1 over 1's 1. So not that big of a deal. Alright, so how am I going to fix this down here then? 2/3 of the way there. I don't need any 1s. I need some... Oh, I don't need 2s either. I need 4 x's and I need a 2x. Can I just put 4x and 2x there? No. As long as you put them... Yeah. So let's... And I need more room, don't I? Let's do this here. Alright, so... So I'm going to put the extra stuff here. So you're telling me that I need what right here? 4x. So you tell me to put a 4x right there? We alright with that? This needs a 2x. Put a 2x here. Make sense? But hold it. These x's just cancel. I don't even need those, do I? If you think about it, putting an x here would have taken care of putting the x there, right? Does that make sense? So here again, now I'm going to write this out the long way. Here is why what I'm about to do is going to work. If I do the limit of the first fraction, multiply it by the limit of the second fraction,
Have your attention, please. We have messages in the office for Tracy Evans, Daniel Williams,
and then multiply it by the limit of the third fraction.
Rogers. The message for Tracy Evans is for the student. Thank you.
So what's the limit of the first fraction? 1, 1, and 2. So the answer is 2. All right.